Okay, so now we're going to look at how soaps and alcohols are in water and also in nonpolar compounds. And we'll look at some salts that dissolve in water. So here we go. Let's get started. So start with our question. So why do alcohols and soaps dissolve in both polar and nonpolar compounds? I'll let you pause the video and come up with some good ideas on your own. And then when you're done, let's see how you did. Okay, assuming that you did pause the video, what I have here are structures of alcohol and a little bit longer chain that we can use to represent soap. So alcohol is a compound, C2H5OH. We can recognize alcohol by its small carbon chain here, and then OH at the very end. Okay, so what do we have here? Well, here's our carbon chain. The gray represents carbon, the white represents hydrogen. And I'm going to put a bracket around this part here. Okay, and this is our hydrophobic part. And that means water fearing. It doesn't like water, and nor does water like it. And then this part here is our hydrophilic, which means water loving. And if you look, I put a couple water molecules in there. The water molecules are attracted to this part of the molecule right here. And this part of the molecule, the water doesn't like it at all. Let's take a look at our diagram for our soap. This is just representative of what a soap would be, a very long carbon chain. And again, we have this part here, which is our hydrophobic, as we've said before. It does not like water, nor does water like it. And this part here is our water-loving part. So we see where the oxygens are. Water really likes that. Why? Because there's something in common with it. So how do these work? Well, the hydrophobic part in both of these dissolves in nonpolar, but the hydrophilic part dissolves in water. So if you look at the soap molecule here, this part of the molecule will dissolve in dirt and oil and grease, while this part here will dissolve in water and wash that away out of your clothing or off your hands or something like that. So that's how those work. The next part of the video is reactions of salts and water. We'll need to properly draw the compound out and then write its reaction in water. So here we go. Lithium acetate in water. Let's do the first one together. So lithium is in group 1, so I'll write Li. And that'll be a positive 1 because it's in group 1, plus 1 charge. Then I go to acetate in my polyatomic ion charts, the first one, C2H3O2 and minus 1. So then I write that C2H3O2 minus 1. Now those charges are both the same, so we don't need to crisscross that. So then I'm going to write that as a solid. Now let's see what happens when they dissolve in water. Well, that'll produce an aqueous lithium positive 1 ion. And I'll write AQ with that, plus an aqueous acetate ion, C2H3O2 minus 1, and aqueous. Okay, so let's try the next one. I'll let you try it by yourself. What about sodium fluoride in water? So go ahead and pause the video. See if you can write the proper formula for it and then its reaction in water. Okay, let's see how you did. Hopefully you paused the video now. Let's see. We've got sodium fluoride. So sodium is in group 1, so that's Na. And that'll be a plus 1. Now fluoride is not listed on our polyatomic ion chart, so that must be on our regular periodic table. And there it is, F. So that's going to be F, and that's minus 1. And that'll be a solid. We don't need to crisscross charges because they're the same. So that's going to break into a sodium positive 1 aqueous ion plus a fluoride minus 1 aqueous ion. Okay, let's try the next one. So we'll click on that. Once again, pause the video and see what you can do with potassium carbonate in water. Okay, let's see how you did. And potassium is in group 1 here again, so that would be a K, and that's a plus 1. Carbonate will not be on the periodic table, it's in our list here, and carbonate here is CO3 minus 2. So I'm going to write CO3 minus 2. We do need to crisscross the charge here. This 2 needs to come down here. Okay, and I recommended that you always put a parenthesis around your polyatomic ion so you don't get confused. We will cross the 1 down here. Okay, now we don't write 1s. You can write the 1 if you want. So what will this make in water? So let's put a solid next to that. So that's going to make 2 aqueous +1 potassium ions. And that's an AQ there. And plus an aqueous carbonate ion, CO3, -2 aqueous. Okay, and there you have it. Okay. Let's go ahead and try the next one. Reaction of calcium chloride in water. Once again, pause the video and then make an attempt and then restart. Okay, let's see how you did. So calcium chloride in water. Calcium is in a group 2 here, so that's Ca. And that'd be +2. And chloride is not on the polyatomic ion chart, so it must be in our regular periodic table. There it is, Cl. That's one you know pretty well. So Cl, that's a -1. We crisscross charges and put a 2 here. The 1 would go down here, but again, I don't write 1s there. Okay, so that's going to be a solid, and that'll break into a calcium +2 aqueous ion plus 2 chloride -1 aqueous ions. And there you go. That'll be the reaction for that one in water. And let's do one more final example. Right, the reaction of sodium sulfate in water. Well, one more time, pause the video, and let's see what you come up with. Okay, let's see how you did. Sodium is on our periodic table right here as Na. So I'll write Na +1. Okay, sulfate is on our polyatomic ion chart. Okay, it is right here, SO4 -2. And again, I recommend you put parentheses around that. We will cross this down here to be a 2 and place a solid here. Let's go ahead and see what this reaction would do in water. I see you're going to have 2 sodium +1 aqueous ions plus an SO4 -2 aqueous ions. And that's how we do our ionics in water.